Good morning, Doctor. We are from Mathematics for Engineering Technology 2, BNR 17903, Section 7, Group 1. Today we are going to present about our group project, and our lecturer is Puan Cik Sri Mazura binti Muhammad Basri. Our group members consist of me, Mackenzie, Kirk Ming Teng, Tan Po Zeng, and Wan Ukail. Now I will pass it to my teammate Kirk to explain about the introduction.
Thank you. Now I will present about the introduction. Differential equations play an important role in understanding physics and engineering. A differential equation is any equations that contain derivative, either constants or partial. In this project, we focus on Newton's law of cooling and the motions of mass. Newton's law of cooling helps us know that the rate of change of an object temperature is proportional to the temperature difference between the object itself and the temperature of its surrounding. The motion of a mass is a second-order linear differential equation derived from Newton's second law of motion. It helps us to understand the behaviors of the system and key physical properties. This project not only let us understand theoretical mathematics but also connect it to our real life. That's all for me. Thank you.
Thank you, Kuming. Now I present for the part of methodology. For the first, we need to overcome an idea generation. For the first idea generation is investigate the theory of Newton's law of cooling. For the second, we need to investigate the principle of string mass oscillation system. For the third, we need to apply the Laplace transforms to solve second order linear ODEs. For the fourth, we need to utilize artificial intelligence, which is AI engines, to facilitate finding of solution. For the last, we need to explore physical assumptions like perfect insulation, ideal spring, no air resistance, and others. For the second, we need to find out the topics and issue that we need to learn for these two problems. For problem 1, which is Newton's law of cooling, and the differential equation is the first order separable ODE. So we need to know about the theory of separable method, the condition to utilize this method, the correct way to utilize this method, the mistakes that are often made when using this method. For the problem 2, which is about spring mass system, there is the second order differential equation. We need to solving homogeneous linear ODE by using the theory of homogeneous equation. We need to know the conditions to use this method. We also need to know the correct way to use this method, the theory of Laplace transform and inverse Laplace transform, the conditions to utilize Laplace transform and inverse Laplace transform, and the mistake that usually made when using all these methods. For the third, we need to come out an information seeking plan. For the step 1, we need to understand the problem by read the question 1 and 2. From the question, we need to identify what the question wants us to do by refer to the provided document. For the second step, we need to do a review of Newton's law of cooling. We can learn about the first order differential equation and exponential decay. We can usually find out the review of Newton's law on lectures, notes, and watch online lecture video through YouTube. For the third step is learn spring mass theory. We need to understand the homogeneous ODEs and harmonic motion by reading the online article or using MIT OCW to searching for the theory. For the fourth, we need to apply homogeneous solution by solve using characteristic equation by using the manual calculation. For the fifth step, we need to learn the Laplace transform by study transformation rules and inverse operation by using the YouTube platform. For example, we can look at the Sri Mazura channel to searching for the learning materials. For the sixth is solve using Laplace method. We need to translate ODE into algebraic equation and apply inverse transform by manual calculation. For the last step, which is validate and compare methods, we need to check the consistency of both analytical methods by compare the answers that calculated manually with the help of tools like DeepSeek and ChatGPT. Now I will pass to my teammate Mackenzie to continue.
Okay, thank you, Tan. Now I will present about the result and discussion. Our first question is, 10 minutes after being served a cup of Milo, it is still too hot to drink at 72 degrees Celsius. 4 minutes later, the temperature had dropped to 68 degrees Celsius. Your friend, whose coffee is also too hot to drink, speculates that since the temperature is dropping an average of 1 degree per minute, it was served at 82 degrees Celsius. Was the actual serving temperature hotter or cooler than 82 degrees Celsius if the temperature is 21 degrees Celsius? Use Newton's cooling law, dt over dt equals to negative k bracket T minus m bracket, where T is the temperature of the body, m is the temperature of surrounding medium, and k is a constant. Now by looking at the equation, we can use separable method, and we will separate the dt and the d capital T, and we will get negative k dt is equal to 1 over T minus m dt. By integrating both sides, we will get ln bracket T minus m is equal to negative kt plus c. By arranging the equations, we can get T minus m is equal to exponent power c times exponent power negative kt. Now we will let a to become ec to make the equation simpler, and we will get the final equation is T is equal to a exponent power negative kt plus m. We know that at initial temperature, the T is equal to 0. So by substituting the value inside our equation, we will get T bracket 0 is equal to a exponent power k bracket 0 plus m, and we will get a is equal to T bracket 0 minus m. Now we will substitute the value of a into our equation earlier, and we will get T bracket T is equal to m plus bracket T bracket 0 minus m bracket exponent power negative kt. We know that at T is equal to 10 minutes, the T is equal to 72 degrees Celsius. By substituting the values inside our equation, we will get exponent power negative 10k is equal to 51 over T bracket 0 minus 21, and this is our first equation. And we also know that at T is equal to 40 minutes, the temperature is equal to 68 degrees Celsius. By substituting the values inside our equation, we will get exponent power negative 14k is equal to 47 over T bracket 0 minus 21, and this is our second equation. By using the second equation divided by the first equation, we can get k is equal to 0.0204 per minute. By substituting the value of k into our first equation, we can get T at time equal to 0 is equal to 83.54 degrees Celsius, and this is the original temperature of the drink. In conclusion, the actual serving temperature is hotter than 82 degrees Celsius, as the result that calculated shows the initial temperature of the drink is 83.54 degrees Celsius. Now we will move on to the second question. The equation of motion is governed by x double dot plus a over m times x single dot plus k over m times x is equal to f bracket T over m, where m is a mass, a is resistance, k is a spring constant, and ft is an external force. Suppose that a mass of 2 kg is suspended from a spring with a known spring constant of 8 Newton per meter and allowed to come to rest. It is then set in motion by giving it an initial velocity of 1 meter per second. Find the position of the mass at any time if there is no external force and no air resistance. Use A. Homogeneous equation, B. Laplace transform. Now we will solve the question by using homogeneous equation. Since A is equal to 0 and Ft is equal to 0, we can simplify our equation into x double dot plus k over mx is equal to 0. By substituting m is equal to 2 and k is equal to 8 into our equation, we will get x double dot plus 4x is equal to 0. By assuming xt is equal to exponent power rt, then we will get r is actually equal to plus minus 2i. So we will get our new equation, xt is equal to a cos 2t plus b sin 2t. By applying initial conditions, which means x bracket 0 is equal to 0 into the xt equation, we will get a is equal to 0. Now we will differentiate our xt and we will get x single dot t equal to negative 2a sin 2t plus 2b cos 2t. By applying the conditions of x single dot bracket 0 is equal to 1 into the equation, we will get b is equal to 1 over 2. Finally, we will get our answer, xt is equal to 1 over 2 sin 2t. Next, we will solve the question by using Laplace transform. First, we will use the Laplace transform on x double dot, and we will get s squared times xs minus sx bracket 0 minus x single dot bracket 0. And by using Laplace transform on x, we will get xs. By applying these two Laplace transform variables into the equation, we will get s squared times xs minus s times x bracket 0 minus x single dot bracket 0 plus 4 xs is equal to 0. By substituting x bracket 0 is equal to 0 and x single dot bracket 0 is equal to 1 into the equation, we will get s squared times xs minus 1 plus 4 xs is equal to 0. By simplifying the equations, we will get xs is equal to 1 over s squared plus 2 squared. By using inverse Laplace transform on xs, we will get the final answer is equal to 1 over 2 sine 2t, which is the same answer that we obtained from the A by using homogeneous equation. Now I will pass it to my teammate 1 to explain about the conclusion.
This project applies differential equation to solve two real-world problems. In problem 1, we use Newton's law of cooling to calculate the actual serving temperature of a hot drink. The result showed it was 83.54 Celsius, which is hotter than 82 Celsius, proving the assumption based on average drop was incorrect. In problem 2, we solved a spring mass motion using both the homogeneous method and Laplace transform. Both method gave the same solution, which is xt equals to 1 over 2 sine t. So this shows that mathematics helps explain and predict real-life systems like cooling and motion accurately.
That's all from us. Thank you very much.